Okay, we are off and running. Lecture 12. This is the second part of a three-part lecture on binary search trees or binary trees in general. So we're going to kind of get into the code today. And, you probably wonder, what is it I'm supposed to learn here from all this stuff? If you were taking a discrete math course, and some of you have or probably will, if you're thinking about computer science as a degree, you'd be studying binary trees as well. And you'd be studying a lot of the theory and the strategy and even some of these algorithms and some of their mathematical ramifications. But we're a data structures and algorithms class, and so we want to cover both sides of it, the coding part and the theory, and kind of keep that a little bit balanced. So in line with that, today we're going to dig into the code on binary trees, and I would like you to be able to understand it. So if you see the code on a test, you can understand what it's doing, or you can kind of read the code and kind of go, oh yeah, I remember this. But I'm not really expecting you in this class to write the code for a binary tree from scratch. So our labs kind of will serve to help build your understanding of that kind of material. So we're going to go through a lot of code today, and I do hope you'll try the practice problems, but you can kind of, maybe take a breath and realize you're not going to be asked to write all this stuff from scratch. Because these binary trees, especially the binary search trees, are like little machines. They really are not trivial to get up and running all in a perfect way. So as we go through this lecture and the next one, you're going to see a lot of code, but don't let it throw you too much. Try to keep up, but don't worry if you're like, gosh, I don't know that I could write that from scratch, because we're not really trying to get that out of you for this. So we got our lab 11 this week, no lab 12. So I kind of blew that up. I was thinking of putting one in there, but nothing for today. So you can kind of take a breath, work on your homework, do what you got to do for Monday, because we got, of course, our homework 3 due on Monday. And then we've got our quiz 3 that goes up to, but does not include today's lecture. So there's still a good deal of stuff there on quiz 3. So I know you got a lot going into the weekend, so we'll take a little spacer today, no lab. And I know lab 11 was a little tricky too. So don't give up on that one too soon. If you kind of got it right and you get stuck, just submit it and ask me for guidance, and I'll give you some hints. Maybe you can kind of knock that out over the weekend. Don't forget about our Quizlets. They will help you kind of with the memorization component of this class. As we go forward, they're going to have more and more stuff that we maybe don't have to outright memorize, but having it quick at your fingertips is going to help you. So hopefully these Quizlets kind of are another avenue if that's the kind of way you like to study. So remember, that stuff is out there. So today we're going to look at how we use these binary search trees to find stuff. So we're specifically looking at a binary tree that's been organized in a particular way so that information is very fast to retrieve. That's our big goal for using these. So we want to be able to insert, not in a random way, but in a logical way. We touched on this last time, so we'll look at the code today and work through it, and then come back and write the code for actually finding nodes by value in the most optimal way. And it's not particularly challenging. It's just dealing with the pointers, but we'll look at that. And then a few other important kinds of things that you'll be asked. How do I find the smallest node in a binary search tree? How do I find the largest node in a binary search tree? These are classic questions that come up in a class like this, and possibly in an interview, right? It's a great interview question. Hey, I got a binary search tree. What is your algorithm for finding the smallest node in the tree? Okay, so you'll see it's not that intimidating of a question once you know the answer. So these are basic things: floor, ceiling, rank. We'll look at those things. And then probably not today, but wrapping up our third lecture in the series will be on Tuesday. We'll look at deleting nodes from the tree, and we'll look at rebalancing the tree as well. So that'll be kind of the third of our 3 parts, and then we'll kind of move on from there next Tuesday. Okay, so those are kind of the topics for today. A couple things to review. We said we could have regular trees, binary trees, right? And we looked at a particular kind here, which is a max heap, which we shoved into an array a week or so ago. And we kind of treated the root or the head as position 0 in that particular array. We're on the binary search tree now, which ideally should be ordered in a very particular way. So we have very optimal access, specifically worst case log n search time to find something at the bottom leaf there, or maybe to find out that something isn't even in the tree, right? That still takes us a log of n kind of thing in a binary search tree, okay? So we'll be writing the code today to do this properly. And remember, for our class, we're going to put duplicates on the left side of the root node. That's going to be an important relationship for kind of those like really nitty gritty quiz questions that might come up along the way. So duplicates on the left side of each subtree, if there are any duplicates, and there might very well be duplicates there, okay? And then we said that, in terms of terminology you want to be familiar with, again, these are common, interview questions. A complete tree, what is that? Oh, the bottom row is left justified. Everything else is filled in. A perfect tree, pretty rare animal out in the real world, but, everything is filled in completely. Unbalanced, we'll start talking about more and more. Yeah, it's a binary tree, but it's not very efficient for searching because it's got this really long branch off to one side. And we'll see some of that today again. That's our worst case scenario with our binary tree, okay? And these two we'll call balanced because you can kind of sense it. They're mostly filled out. You might say, well, this one's not perfectly balanced, but in quotes, they're a lot more balanced than this over here. And we'll talk eventually next week about, well, how do we measure balance? How do we decide in our algorithm what constitutes too unbalanced like this versus something over here? So we could probably invent a few rules ourselves, but there's some pretty standard ones that we'll see next week on Tuesday that describe all that stuff, okay? So that's kind of where we are. We talked last time about depth first, which is kind of recursively traveling through the tree. We said there's kind of 6 different ways to do that. And most of the familiar or popular names describe the position of the parent: in order, pre-order, post-order. So in terms of those crucial 3 lines of code we saw in our print tree method, the order of the parent value that gets printed out, that's kind of the indication of, are we pre, post, or some other order. So just kind of keep that little hint in mind. It'll kind of help you kind of remember what's what, okay? But for better or worse, the names are kind of important out in the real world, even though there's somewhat arbitrary names that people came up with to describe those 3 little lines of code, okay? So it's where the parent sits relative to the children in that scenario, okay? Breadth first was the other one, right? There's just one of those pretty much, and we use a queue to do that. We said, oh, okay, we need a queue. We don't use recursion for breadth first traversal. We know how to create a queue, and then we pull out the node and put its children in. We pull out the 9 and put in the 2 children, and then we just repeat that, and it's almost magical how, it travels through the tree for us. Okay, so you want to keep that one in mind. Sorry, that's a classic quiz question and interview question as well. Okay, so that's our breadth first traversal. So this is, straight out of the quiz and probably potentially straight out of the midterm. It's like if I say, hey, here's some different traversals and a bunch of names over there on the right side. Which one goes with which, right? So pick the one you know best, maybe. In order traversal, depth first in order would be sort of a 3, 5, 6, 9, 11, 13, 21, right? So 3, 5, 6, 9, 11, 13, 21. That should be the in order traversal, etc. So you should slowly be able to, through process of elimination, figure out which one of these goes with which one of these, okay? And so I think our answers here are sort of here, pre-order. That means parent first, right? 9, then the children, right? 3, 6, 5, right? Or 9, 5, then 3, 6. So parents first, then children, and etc. Okay. So those things you should be able to kind of noodle your way through, process of elimination, figure out which one kind of goes with which name. Okay. And obviously that means you kind of got to know what out of order means and what post order and in order means. So you have to kind of put those two slides together to kind of sort that stuff out. Okay. Now last time we kind of said, hey, here's how we're going to wrap up everything neatly in a box. And in this case, the box is a binary tree that points to a kind of linked list of nodes, but it's a binary linked list. So it's sort of floating off to the side of that box. And we're going to dynamically create instances of those nodes to sort of build up that tree as we go. So we kind of brushed off our C++ pointer stuff last time and said, okay, when I say new, I always get a pointer, right? So I'm getting a pointer to a box of stuff, right? So there's my BTPTR pointing to a box of stuff, and that stuff has a null pointer, right? That's the head pointer, and off we go. We'll be inserting into that thing to hook nodes up and hook it together one by one. Okay. Now there's a few ways I could do this. Sorry, this is a little off the screen. I could do it all on one line or two lines, we said. So if you see those two things, they're really the same kind of thing. We're just calling the constructor, passing in a value, and then inserting. Whoa, something's wrong with my constructor here. I just noticed a typo. Sorry, folks. This does not need to be there. That is a mistake. Sorry. So I'm not passing any arguments into the constructor. I'm passing them into the insert. So that's a little typo. So apologies if that confused anyone. I don't know how that got through. But there's our insert with our I node. Okay. So that's the one we're calling there. Okay. And now we have our 13. Okay, so we'll kind of dig into some more code and slowly, hopefully, get you a little more comfortable with all this notation. Hang in there. And just keep in mind, for those of you who are a little more comfortable with C++, it's an interesting question. When I say binary tree BT2, it's like saying int x. I'm like, hey, give me a binary tree. And you might think, well, wait a minute, what's the difference between that piece of code and this up here? They're pretty similar. It's just that this BT2 down here is not a pointer, it's an actual box. And so I can say BT2 dot something, where up here, because this is a pointer, I say BTPTR arrow something. Okay, so this is the difference between in C++ creating the thing or creating a pointer that points to the thing. Okay, I don't mean to lose anybody on that, but we will probably do most of our work in this domain for this class because we're doing a lot of dynamic construction. But every once in a while, people say, why don't we do it this way? Okay, so some of you who've taken a lot of C++ might recognize the difference. The rest of us, don't worry too much. I'll just help you guys with that syntax as we go forward. Okay. Oops. Get my arrow break thing back up there. All right. So off we go then. Print tree, we said, hey, you know, the order of these three lines is everything. Swapping that order around achieves all 6 different kinds of depth first traversal. So it's really just the order of those three things that determines what kind of traversal you're doing. Travel down the left path, then pop back up, travel down the right path recursively. And it's not a linear process. So we have to imagine these little branches being kind of explored and then rewinding up the branch every time. Okay. So is this breadth first? No, it's depth first. We're going all the way to the bottom and then back up slowly to get where we need to get. Okay. Is it pre, post, or out of order? Well, the parent is in the middle here. So that is an in order traversal. Okay. We call that an in order traversal. Now, when we insert in a binary search tree properly, we do it according to whether something is less than or greater than a current value. What we saw last time as a warm-up was randomization. Flip a coin and decide whether you want to go left or right. So this is not a very realistic thing. We wouldn't normally do this out in the real world. We're just sort of simplifying our kind of starting code base before we kind of move off of that today. So today we'll kind of rewrite this thing pretty quickly and do it the right way, rather than just flipping a coin and just plugging it in at the left and the right. Okay. And remember that this is a recursive call. It's like, hey, you take it from here. Here's I. Please explore down the left path and keep going if you got to keep going. So it's going to keep going either left or right at every stage, depending on that flip, until it gets to an empty place where it can plug that thing in, right? So it's not inserting anything up here in this structure. It's trying to find a leaf where it can plug it in at the closest position. And at the moment, that's random, but we're going to change that here pretty quickly. Okay. So we saw that last time too. Okay. Let's this is, let me camp out on this just a little bit longer for those of us who have not had a lot of recursion. So notice that when I come in here and I look to insert, if I end up in a situation where I need to kind of continue and I flip a coin, right? Because I'm at 9 and these things aren't null. I'm going to say, okay, I'm flipping a coin. Let's say I'm going left. Remember that when I go left, I'm sort of passing this pointer, which is this pointer down, okay? So this pointer becomes the starting pointer when we drop to our next level of recursion. Okay, so we're trying to insert the 7. Now we're starting from that particular pointer and saying, okay, which way do I want to go to find a leaf? Okay, this time we flip the coin and we go right. Okay, that's just a random thing, but we're passing this pointer down to the next level of recursion. So now we're back up again in another copy of the function. Remember, recursion doesn't just reuse the same function all over and over again. It's a copy. So we're now 3 levels deep with these other 2 copies above us waiting for us to unwind. Okay. So always hard to visualize that. But remember, we're not doing the loop here. We're going deeper, deeper, deeper. So now we're finally here and we found that the left node of this is null, right? It's null. So we're just going to plug in a brand new node, right? It's like, okay, we flipped a coin, we plugged it in, game of chance, that's where it ended, right? And then we unwind all the way back up the stack, okay? That's the only way we get back to the surface is by unwind, 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 okay? And those other functions are still waiting around. So when I return from this particular part right here, which happens at the very bottom, I'm going to go back to where I was called from the previous level and then back and back again. Okay. So it's a lot to keep in your head. Just be sure we're not doing a loop here. We're actually burying ourselves under deeper and deeper copies of that same function. Okay. So let's see if we can take it up a notch and implement ordered insertion in that code. And so remember, the process is if the current node is empty, insert at the current node, right? That's okay. We can put something in there if we want. Otherwise, we're going to either insert left or we're going to insert right. So if the node we want to insert is less than the current node, well, we're going to go left, right? Or less than or equal to, because duplicates go on the left side. Otherwise, we will recursively insert at the right. And we just keep doing that recursively. So we got a 1 and then an 8. 8 is greater than 1. So we plug it right into the right child. We don't even do any recursion. It's just like, there you go. There was an open spot. That's where it goes. 9, where does that go? Okay, well, we're going to have to go down the path, right, to the right to find an insertion place. Always starting from the root every time we insert, right? Start at 1, go right, right, right. We got another 9. That's going to go to the left because duplicates go to the left. So we search greater than, less than or equal goes over here. Okay. And we'll look at this code here in just a second. Another 9, kind of see how it's going to go. 8, duplicate goes over there. Okay. Always starting from the top. 0, where should a 0 go? 0 is less than or equal to 1, so we plug it into the left child. And on we go. A 1, what do we do with a duplicate? Well, it's less than or equal to 1, So we plug it in on the greater than side of the 0. Okay. So that's going to be our algorithm. And we hope it will build a balanced tree. But as we can see, it kind of depends on the insertion order. We didn't do too badly here. If that thing were a coat hanger art or something hanging from the ceiling, it would be okay. But sometimes we get a worst case scenario, right? So 7, 9, 0. Okay, this one's actually relatively balanced as well, so it's not too bad. We'll go run through a couple of these real quick. But you can see that the order in which I insert them changes the shape of the tree that I get. It's not immediately obvious if you haven't worked with binary search trees before, but the exact same numbers inserted in a different order is going to create a different tree. Okay, because of the way we're going to be doing this. So here's just another example, 4810880, couple zeros, we get something like that. Okay, and these are slightly different trees, but they just show you some of the patterns you can get, not all particularly ideal. It really depends upon the order. Okay, another one, 544371004, right? This one's not too bad. Whoops, too far on that one. Okay. And then a couple, I think I got some worst case scenarios here. Right. So watch what happens here. If somebody gives us our numbers in order, that's actually a bad thing for binary search trees without something special. It's just like we just keep doing what we're supposed to do, which is inserting it out to the right, and we get this very nasty long thing out to the right. Not a very nice tree. So there's no guarantee that the insertion code we're going to write is going to create a balanced tree. We're going to have to learn about balancing on Monday. But we are going to start out by building a valid binary search tree at least. And then we'll come to the balancing part on Tuesday of next week. Okay. And of course, if it's a descending list, it's just as bad. Okay. So the most ideal list kind of starts with the median value, right? The middle value would be the best root of our binary search tree, because then we kind of know that that would be balanced on the left and the right side, right? But in order to find the median value, we kind of have to sort our data, which is the whole point of inserting into a binary search tree. So we really can't count on our data being in a nice way. So we're going to have to build a machine, a binary search tree, a balanced binary search tree to solve that problem. And we'll do that again. We'll do that, wrap that up on Tuesday. Okay. Lots of ways to insert, lots of outcomes that we might get. Here's one that's not too balanced, right? And if we want to find something, remember that we kind of got to go to the very leaf to figure out that it's not there. So our worst case search is probably the longest chain that we have. And so longer chains are kind of frowned upon if we can avoid them. Okay. So let's do this interactively. Let's jump on visualgo.net if you would like, and make sure that you choose the binary search tree, not the AVL tree. So we'll talk a little bit about AVL trees or stuff similar to AVL trees next week, but we're just going to kind of work with our basic binary tree here. And you can create, I think an empty one is probably the most instructional. And then I think what we want to do is insert some values, 12, 25, 37. So we'll go to insert, and I'll just say 12, 25, 37. You can put all the numbers in, or you can do them one at a time. But I'll just put those first three in. And you can kind of see the algorithm we're talking about. It's just going to figure out whether the next thing goes to the right or the left every time. And we can come back, and add more stuff. So after inserting those, let's say I want to insert 63, 75, 87. So 63, 75, what did I say, 87? It probably doesn't matter. Do that like so, okay? And it'll find the place, put it in there, and it's going to be an unbalanced tree, right? So it's correct, it's valid, just not very efficient yet, and we'll get there, okay? So that's a binary search tree. There's another version of this that is balanced. We'll get to that next week. It's called an AVL tree. There are also implementations called red-black trees. So there's a variety of machinery out there with different names for different kinds of styles of balancing. So we'll get to that stuff here shortly, okay? But you can kind of see if we insert with a median value each time, we actually get a perfectly balanced tree. But no one's going to give you data like that. So it's really not going to, bias a whole lot to get that thing perfectly balanced. So how are we going to do this in code? Let's take a look with our current structure, and then we'll kind of jump into the code here in just a second. So I got 4 cases that I got to deal with. So when I want to insert something, I want to, let's say, first check and see, if the start is null, well, then I know it goes at the head, right? Because it's a brand new tree. So that's an easy one. So that's kind of a given. If it's null, just create a node and plug it right into the head, and we're done right there, okay? Otherwise, if something is already at the head or the root, then if what I want to insert is less than or equal to, then I'm going to try to insert it left. So in this case, where there's no left child, I just plug it into the left child over here and I'm done, okay? Because it should be less than 37. That's our first case. Our second case is if there is a child, then we have to recursively call our function on that as the new parent and go from there. So it's just a recursive step there. And then, of course, ultimately, we have to return back up to the next level. So we're going to try to do that on both the left and the right side and see if we can get this thing inserting, even if it might be a little bit unbalanced. Okay. Whoops. So let's take a look. I'll give you this code, kind of lay it out so you can start. This is kind of the way we always start. If the start is null, then let's plug it into the head. And if it's not null, then we'll just use whatever somebody gave us, because that means we are in the middle of some recursive call, okay? So that part's a little confusing, but it's basically saying, hey, if nobody told you where to start, we're going to start at the head. Otherwise, we must be in the middle of some recursive action here. So just kind of go with the start. So now I want to create a new node for I, and if where we are is null, then just sort of like plug it into the head, right? That's an empty tree. That's our easiest first case, okay? So that's something you want to add to that code if you're kind of following along there. I'll give you a moment to do that. And remember, head is a data member of the class we're inside of. So we're currently inside of the binary tree class. So head isn't some random variable we're supposed to create. It's a data member of our class that's there waiting for us to plug it into a node, right? So that's what we're doing in that case, okay? But what if it's not null, right? So if it's not null, right, else, so this was our previous slide, else if the thing we're trying to insert, I, is less than or equal to the starting value, then we know we want to insert it on the left-hand side. So can we just directly insert it in the left child? Well, yeah, if the left child is null, I can just plug it right in and be done. Okay, and I could even just return right after that, but I do my return at the bottom here. Else, I am going to say, hey, better continue the journey at the left child as the parent. So that sends in the start as the left child, and of course, the process begins at the next level, okay? So that's what's going on the left side, and the right is just the mirror opposite of that. We accept not greater than or equal to, just greater than, okay? Else if I is greater than start, go ahead and do that on the right side. Okay? So that is insert, right? If we step back and look at all the code, that's really all we got to do, okay? So it's this case, right? Or this case where we have a left child and maybe something below it, right? Or it's this case where we got an empty right child and we're supposed to go right. Or we got to recursively go down to that 47 and continue from there. Okay. And keep in mind that we're assuming there's a subtree below that 47, but maybe 47 is the only thing that's there. We don't know yet, not until we recursively drop down and repeat the process. Okay. So let me give you a moment to kind of soak that in, okay? Now, there are different ways to write this kind of code. I wrote it to minimize the amount of special pointer magic you have to do. This is one of the more straightforward ways to think about it, but there are more clever kind of C+y ways to write this code so you don't maybe have as much code on the screen. But I wanted you to kind of see this stuff kind of written out in the four cases. Okay, but that covers it all, and recursion is a beautiful thing because it just takes care of everything else pretty much magically. Okay, and that's it. That's our insertion. So you should be able to get that one up and running so you can insert in the tree and see stuff popping out, kind of like we were. And maybe you're going to get an imbalanced tree, maybe you're not. Kind of depends on the order in which you insert those. Okay. Anybody have any questions from kind of what you were looking at in the code so far? Okay, all right, not too much code, but good stuff to think about. All right, so maximum height. Let's just reflect on this thing for a second. This is just a little bit of math again. Probably you guys are getting tired of this, but it is interesting to know if you have n nodes in a tree and it's balanced, let's say, what is the maximum depth or height of the tree? So if we count height as counting all the levels, that's a tree with a height of 3. So it's only got 1, 2, 3, 4 nodes in it. But could we come up with an equation that says, oh, the maximum length for a binary search tree that's balanced with 4 nodes would be what, right? How could we figure that out? So if I said, hey, I got 10 million nodes, it's perfectly balanced binary tree, how deep is it, right? We would want to come up with an equation for that. It's not too complicated. It's just essentially log base 2 of n plus 1 to kind of make the math more or less come out for a perfect tree. That is a perfect tree where everything is filled out. So if I had a tree of 1, right, that's going to be, 1 plus 1 log base 2. Log base 2 of 2 is going to be 1. That's a height of 1, right? So you can kind of, roll out the numbers. If I have a tree with 3 nodes, it should be a height of 2, right? 1, 2, 3. Tree with 7 nodes, 1, 2, 3, 4, 5, 6, 7. That would be a height of 3. Log base 2 of 7 plus 1. That's 8, right? 2 to the third power gives us 8. So it's kind of just a little teeny bit of math, but it just shows you, we need one more to get to the clean log base 2 answer of how high our tree is. Now, if the tree isn't perfectly filled out and it's mostly filled out, we can still just round up by kind of applying the ceiling function in math to take whatever that rounded number is up to the next highest integer. Okay, so even if it's not a perfect tree, we could still take a 4, for example, and say, oh, okay, 4 plus 1 log base 2, that's 2.3. It's going to be a maximum depth of 3, okay? So we're really just kind of splitting hairs at this point, but it's like, hey, you can build an equation that gives you the exact worst case traversal for any number of nodes in a balanced binary tree, if it's balanced, okay? So normally we just wave our hands around and go, it's log base 2 of n, right? And everybody's pretty happy. But if you really, really, really wanted to like convince yourself that this is where it comes from, that's how you would do it, okay? So hopefully that's not, completely useless information, but every once in a while I'm like, how do I know? I really want to know exactly. And that's kind of the exactly part. Okay. Okay, so let's get back to the code. Let's see how we actually use this nicely inserted node strategy to find stuff in optimal time. So let's just take a quick look, and you guys don't have to do this again, but it's if you've played around with it especially. But if I have a tree, let's say that I've created a binary search tree, not a AVL, and I create it randomly, Okay, so there's a random tree, and I say search, and I want to find, let's say, 33, right? So I'll just change that to a 33 and say find that exactly. And you can kind of see the process. It's going to say, am I less than or equal to? Am I less than or equal to? Am I less than or equal to? Greater than, greater than, and we find it. Okay. So if we build it properly, pretty easy to do that. And we'll see that here recursively in code. Okay. Now you can search for min and max values. We'll actually kind of learn that one here in just a second. But the longest search we need to perform, if it's balanced, should be log base 2. But if it's not balanced, it's going to be n, right? N could be our worst case scenario. Now, we could, and I have seen this, write a find function that always finds what it's looking for, but is really inefficient. So let me show you what kind of happens. If the tree is empty, we know there's nothing. So false, I didn't find it. If the start node is what we're looking for, well, that's pretty easy, right? That's return true. We found it. Okay. Otherwise, if the left branch is not null, then we're going to explore the left branch, right? Purely because it's not null, we'll go left first. That's an in-order traversal. And then we will come back and explore the right until we find it, okay? So we gotta quit if we find it. And that is kind of the first lesson in this particular pile of code. It's like, how do we return so we don't keep looking after we found this thing? So let's look at the code and how we do that. And remember that our traversals are kind of, you know, at our fingertips. We could traverse this tree in any way we want to find the 10, right? So we could use an in-order traversal. We could use a reverse traversal. It really doesn't matter. If we're going to look at everything there is in an inefficient, naive approach, use any traversal you like. You could even use breadth first traversal, right? But we're going to use an in-order traversal, or sorry, pre-order traversal. We're going to say, hey, is the parent it? No. Okay, go left. Okay. Is 5 it? No, go left. Is 3 it? No, go left. Okay. Nope, that's not it. That's not the 10. Okay, I got to unwind. Is there a right child? No. Unwind. Is there a right child? Yes. Go right. Can't go left. Go right, etc. Right? So this is brute force. It's not using the fact that our tree is ordered, but we do eventually find it. And our worst case scenario for that find would be n if it was really all the way over here in the corner, okay? Or worst case, we didn't find it anywhere. We'd have to search everything. So that's not very smart, right? That's why we say it's a naive approach. We're just going to do like we did with our print tree and just kind of explore everything, which is, just getting us started, right? But once we find it, if we know we found it, we do not want to do any further traversal. So if we found it, just return up the stack. Don't keep searching, okay? So the return value for the recursive call now becomes a very crucial piece of information to guide whether we do more recursion. And that might confuse some folks. So we'll look at the code here. So find brute force. Okay, so we'll do the same thing. I'll let you guys click into it and I'll share the code and talk you through it. So let's look at the find brute force function. Okay, so this is kind of everything all in one go, but let me talk you through it. I think I've got some animations here, right? So we do our usual pointer fix up. So we're either starting at the head or we're in the middle of some recursive call where start has already been given to us. And if the thing that was given to us is null, that means we fell off the end of the tree and we didn't find it. So return false. Okay. If the thing we're looking for is equivalent to where we are, then we can return true. Okay. And here comes the tricky part. If the left side is not equal to null, and what we got back from searching the left side equals true, then we can return true. This is the part where I usually lose people. It's like, we do not want to return true unless we actually found that this was a true search down that left branch. And we don't want to go down that left branch if the left branch is null, because we would probably mess up our search. We would be sending a message that we're starting at the head again, and we'd be in an infinite loop, basically. So we need both of these checks to know that it's done, and we can return true up the stack. Okay. Same thing for the right side. Otherwise, we haven't found it, right? We reached the bottom of the pile, or we reached the leaf, and there's nothing there for us to find. Okay. So that is a parent left right, or pre-order traversal. Parent is before the left or right recursive calls. Okay, so a little different than our print tree, but it's the right order for this particular kind of simplified search. Okay, so that's brute force. It works, gets you the answer. It just doesn't take advantage of this ordering that we have kind of worked hard to do. Okay, so let's take a look at the optimal one, and you can probably guess, what this is going to look like. We're going to do the same thing, do the two basic cases first, and then we're going to look left if we can, right? But if left is null, then we know we're done, right? So if the thing we're looking for should be on the left side, but there is no left side, then we're done. It's not here, guaranteed, okay? So if it's null, okay, recursively go search. Otherwise, it ain't here, right? Because it should have been less than or equal to the parent node, but there's no left child to follow, okay? And then the right side is just a reflective thing, reflective version of the same thing on the left. If we can go right, go right. Otherwise, let's go ahead and just return false, okay? And then we get to the bottom, that's basically, it's not here, okay? This is our optimal kind of search path, okay? So it's like this, as you might imagine. We kind of saw it before. It's like, hey, is it greater than 9? Yeah. We're looking for 10. Is it less than or equal to 13? Yes. Okay. So we're going to go left. Is it less than or equal to 11? Yes. Okay. And there it is. We found it. So then we return true up the chain, right? We got to get true all the way up the chain for it to work. Okay. And that's the part where sometimes things get broken. Okay. It's like, think of it as a pail of water. We got to get it all the way up from the basement up to ground level again. Okay. Okay. So we'll look at the code for that. Okay. But we often don't even realize this part is happening. We have to study our code carefully. And sometimes putting the word unwinding at the bottom, and you might want to do this in this next practice, you might be interested to say unwinding from parent number, unwinding from parent number. It's very revealing sometimes to actually add that code. Now, one more thing before we look at the code, you might think, okay, well, how do we estimate the average time it would take to find something in a binary search tree? So one way to think about it is if we count up all of the hops to get to any particular node, like to get to a 1 is 3 hops, to get to a 3 is 2 hops, to get to the 5 is 2 hops, right? It's very tedious, but if we added all those up and then divided by the total number of nodes, that's pretty much our average search depth for an average find, okay? So, there are lots of ways to do that analysis more mathematically, but empirically, we could sort of do it that way, right? Add up all of the possible hops that you could find and then calculate it. And it turns out that sort of for this size tree, it's 22 total hops. If we add up like the orange ones, the blue ones, the white ones I haven't drawn for the 11 and the 12, the orange ones, we got 22 total hops divided by 11 nodes. We're going to average about 2 hops, right? Which is kind of in the middle of our depth. So it turns out that if we did, the full math solution or evaluation on this, we'd see that, the average number is kind of somewhere in the middle of our maximum depth for our balanced binary search tree, which is pretty cool. So we might have a bad day, we might have a good day, somewhere in the middle. We're halfway in the middle of this depth thing. And that's a really great place to be, right? That's pretty optimal. Okay. So let's look at the code for this real quick. This is our find optimal, and we'll kind of then look at a few kind of ancillary features that we want to have. But we want to search left when the target is less than or equal to the start value, right? Search right when it's greater than, and then return false if the branch we choose is null. So let's see how this one goes. Again, you can kind of knock out the code here if you want. But essentially, we do our pointer fix up, check for a null tree, and then we say, okay, if this thing is equivalent to where I'm at, I'm done. Easy answer. Okay. Now remember, I could be 10 levels deep in recursion right now. So this return true might just be going up to the previous recursive level, which then needs to go to the previous recursive level, etc. Okay, so keep that in mind. Here's finding it at the left if it belongs on the left, and doing so recursively. And here's the key bit. We don't just say find optimal, we got to say return find optimal. So let's think about that for a minute. If it's less than or equal to the parent's value, this thing that I'm trying to find, it's either on the left side or it's not. So I'm going to return the answer to the question, do you have I in your subtree? Yes or no? That's the final answer. So we don't need to do anything else except just pass that up the recursive stack. Okay. And then otherwise, if that's null, then we know it's not there. So we're going to pass a false up the recursive stack. And then the right side is just the mirror reflection. The else is like, hey, it should be on the right side. So do that similar kind of thing. Okay. And that pretty much covers our cases 1, 2, 3, 4, and 5, if we want to number them that way. Okay. A lot to take in, especially trying to visualize these trees. But once you kind of got that handled, you got a bulletproof insertion algorithm there, which is pretty darn cool. Okay. And we will always return a false at the end if we ever fall through all of our cases, right? So that's always a good thing to have. If my function needs to return a bool, do yourself a favor and just return something at the bottom and then write your logic on top of that. Because if you accidentally don't do that, you get some really bad errors in C++. So that's a nasty one. Okay. So I always try to put a false in there or something and then change it if I need to. Okay. So there's our recursive calls. Okay. All right. Any questions on that? Okay. I know this is dense stuff. Again, don't let it blow you away. It's just we want to get a sense of what the code looks like to go with the algorithm. All right, let's do a few fun ones. This one's not so bad. How would we find the minimum recursively? So if I give you a pointer to a tree and I say, hey, what's your algorithm? Write the code, right? I give you all the other code and I say, could you write me a function that gets the minimum value? So it's simply going to be keep going left as long as we can. And once we can't go any further, just return that value 1 up the stack. Okay, and we'll look at the code for that in a second, but it's good to kind of try to visualize that. First, we check the tree. If it's null, then we check and see if there's nothing there or if there's one thing there. So let's take a look at what that code looks like. Okay. So get minimum node. Okay. So we want to return null if the head is null, or return the current node if the left is null. If I don't have any left children, then I am the minimum value by definition. Okay. If my left child is null, I am the minimum value. Okay. Otherwise, go left. Recursively go left. Okay. And we're using a negative value in main to trigger that for those of you who are doing that. So if you want to find something after you insert it, just type -5 and it will try to go find that. It's a little hacky, but so let's take a look at this one, right? So fix up, check for null. Okay, if it's, notice here, we're not returning true or false here. We're actually returning a pointer to the node. This is a really powerful thing because it gives me the capability to do something to that number after the fact. I'm literally getting a pointer to the node, not just a true or false value. So if I can't find it, I return null in this case. And if left is null, then I am the minimum node. So return me, my pointer, right? I am the minimum node, and that contains the minimum value. Okay. Otherwise, we're going to search right and return the minimum, or sorry, return the minimum, not on the right, on the left, the next level down to the left. So we're just searching left, 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 left. Okay. Again, if you forgot to put a return there, it's not going to work because we got to return a pointer in order to satisfy our return value here. Okay. And to be safe, you could always just put a return null right down here, just so the compiler never screams at you and you never have a crash bug. But we've got pretty bulletproof code here, so we're in pretty good shape. So that's our get minimum. You can imagine that the get maximum is the same. We won't go through that code, but we're just searching right, right, right. So here, notice 13 is the maximum. So we go right, not left, because this stuff is all less than 13, okay? It's between 13 and 9. So this would be our maximum node right here, okay? So each of these questions, of course, challenges our ability to think about and write a recursive function that processes this in the tree. So that's what we're really kind of after with all this stuff, okay? How could I do that? Okay. Now, if I want to know last two or three things here, we'll get you guys done a little bit early. So if I want to know what is the minimum thing on the right side, right? So what is the minimum thing on the right side? Seems like a strange question, but it's going to help us do some good stuff on Tuesday next week. So I kind of got to do a one hop right. It's like a dance. Do a one hop right, and then what we were just doing, find minimum. So I can literally use my previous function to find the minimum on this tree. So the answer to the minimum on the right side is just to find minimum on the right child, and we're done. So that previous function solves the problem for us pretty easily. We just sort of give it the right child, assuming we have one, and let it do the recursive searching, okay? Same thing for finding the maximum on the left side. If we want to find the maximum on the left side, we take a one hop left. I can't believe these things are sneaking through here. One hop to the left, and then call get maximum on that side over there. And we're done. Okay. So you might think these are like, who cares? But if you are using the map library in C++ or equivalent library in Java or dictionaries in Python, this is what you're doing. You're using a binary search tree to get an ordered result from your stuff that you stored. So it's pretty standard stuff, and we use it most of the time. Okay, so get ceiling. These, I'll just kind of breeze over these, but these are the canonical things. Like, people will say, hey, what does it mean to get the ceiling of something in a binary search tree? So just so you know what that means, if I say, what is the ceiling of 7? Well, if you look at this tree, you'll be like, I don't see a 7 anywhere. But what I'm asking you is, what's the nearest thing greater than or equal to 7? Okay. So how do I find that? Well, I got to go searching, and eventually I should find the 8. Okay. It's like, hey, 7 is less than this. It's greater than that. It's greater than that. Oh, I ran out of space, but I found you an 8. Okay. There's your answer. Okay. So that's what the ceiling means. Ceiling of 10 is 10. It's greater than or equal to the target. 14 is undefined because there is nothing greater than or equal to 14 in that tree. So that's what a ceiling means in that case. Ceiling of 2 is a 3. 2 doesn't need to exist. 0 doesn't even need to exist to find the ceiling of 0 because it's the closest value greater than or equal to 0. Okay. So these are standard defined operations on a binary search tree. I wouldn't bore you with them otherwise, but that's what a ceiling is for us. Okay. So it's an interesting question, like how would I do this, right? How would I write the code for that? Okay. And another way to just think about it is if you lay the numbers out in sequence, the ceiling of 7 is the next thing in the in order traversal of that binary search tree. It's the 8. So that makes it maybe a little bit easier to visualize. What's the next greater than or equal to thing than a 10? It's a 10, etc. So same things we saw last time, just viewing it via an in order traversal instead of the full binary tree. Okay. Ceiling of 0 gives me the 1. Okay. I don't know if I have the code for this, but the algorithm is if the target is equal to the current node, well, then just return the current node. Okay. That's an easy one. Otherwise, if it's greater than, then return the ceiling from the right child, if there is one. Otherwise, return null or undefined. Okay. So we recursively just keep looking and looking and looking. Okay. And then same thing, if it's less than, we go the other way. All right. So it's not too different than a search. We just have a little slight change to the code. And then get floor, same thing. It's just searching in the other direction. Okay. So, whoops, sorry. So floor of a 6 should be a floor of a 7 rather should be a 6. So we'd have to write recursive code to kind of search through to do that. Okay. Good practice problems to come back to. But I'm not going to ask you to write that code, but I am going to ask you to understand what floor and ceiling mean, because it's kind of just part of the language of this particular data structure. Okay. So here's just another way to look at floor of a 7. If it's an in-order traversal, it's a 6. Floor of the 10 is equivalent to 10. So you get the 10 back. Floor of the 0, undefined, because there isn't anything, etc. Okay. So hopefully that's not too simplistic. Just want to make sure you see those operations. Okay, just a couple more. And this is the algorithm. I'll just kind of put it up there for a moment. But basically, we're just kind of flipping the direction a little bit. And I think the code will be there for you to look at, but I don't think we're going to write it. Okay. The one we are going to write, this is our last one for today, and then no lab again. So I think this is our last one. How do we count the number of nodes recursively in a tree? So if I give you a binary search tree, how are you going to do that? It's a fun one. We'll do that here in a second. But let's just review the definition. If I say, hey, this is the whole tree, how many things are in it? It should be 10, I think. Is it 10, actually? Yeah, it's 10. Yeah. 1, 2, 3, 5, 7, 8, 9, 10. Okay. So if I check for B, the size of that is 4, including the 13, right? And the size of D is a 1, and the size of C is a 2. Okay. So that's the definition of size. But how would we write that code recursively? It's not too hard. It just maybe takes a little bit of scratching your head. So the left side is the size of the left tree. So that's our recursive part. It's like, hey, I don't know how big you are. You tell me. Call the recursive algorithm. Okay. And if it's null, then the answer is 0. Okay. So that is our base case for the left side. Right side, same thing. Recursively call. Once I get to a 0 or a null, then that's a 0. But if we're going to unwind, before we unwind, we got to pass the answer up. So the answer is going to be the left size plus the right size plus me, 1. So I'm a 1. And that's going to be our kind of get size algorithm. And this will become interesting for our balancing that we're going to do next week. We kind of need to know whether you can imagine like a branch on the left is massive compared to a branch on the right. Okay, so getting the size of these things, maybe after some edit operations, is kind of important. The whole tree, we can keep track of the size, but if I want to jump to an arbitrary branch and go, how big are you? Well, this is a helpful little operation to have. So let's see if we can write this one. This will be our last one. So it's not a lot of code. Okay. So find your get size method in there. Okay. And we do our usual pointer fix up. We're going to need a little variable here. Okay. We could write it differently, but I kind of made it a little clearer to read. If the head is null, or if the start is null, then assign it to the head. Otherwise, just check it, and we could be at a leaf node. So if we're at a leaf node, then return 0, because there's nothing here. Okay. Otherwise, if the left is not null, then calculate the left side recursively. And if the right is not null, calculate the right size, and then return 1 plus the left size plus the right size. Okay. And that's your kind of recursive adding up all the nodes. And there's probably other ways to do that. Certainly with less code. I just kind of did it that way so you can maybe read it a little more explicitly. So that's our get size, right? Recursive stuff. Now, the last one I'll just mention is rank. This one comes in very often, but the rank is like, hey, what order are you? What order is a 7 if we laid all the nodes out in order traversal? So this is a fun one to write too. I don't think we'll go over it here today, but the rank of the 7 would be a 4, right? 1, 2, 3, 4, right? How many nodes are less than the target value? That's the definition of rank. Okay, what's the rank of a 7? 4 nodes before it. What's the rank of the 10? 6 nodes before it. Okay, 1, 2, 3, 4, 5, 6, not including the 10. That's what we mean by rank. What's the rank of 0? That's going to be nothing. Okay, and so on. Okay, whoops. So those are the major operations you would want to do on a binary search tree. And we looked at most of the code for them. And, again, don't need to memorize it, but you should kind of recognize what it's doing if you see it, because you'll probably see it on quiz 3 coming up. Not quiz 3. Yeah, wait, what's the quiz on Monday? Quiz 3 or Tuesday? That's quiz 3. So quiz 4, you'll see this stuff on quiz 4 and the midterm. So you'll definitely want to take a peek at quiz 4 when it's available, which is coming up pretty soon. Okay. And you can study all of these on the Quizlets if you just need some quick review. Yeah, they'll be on quiz 4. And this is the ungraded quiz, by the way. This is a freebie. It's just a practice quiz before the midterm. So don't let it stress you out too much. It's kind of an extra opportunity to just kind of get yourself oriented before the midterm. Okay? But these are our main operations: min, max, size, ceiling, floor, etc. Okay? And that is that. So hopefully we can get you guys out of here a little early. For those of you who want to go through any of your homework stuff, I will stay until you're all done. Otherwise, I'll see you guys on Tuesday, and have a good weekend. And send me your code if you get stuck, all right? Don't hesitate to email it to me if you need me to get you unstuck, all right? Thanks, everybody.